environment like Titan, which is at minus 290 degrees Fahrenheit. So it's a cold environment. And in fact, you might very well want to have the increased reactivity of arsenic in that environment just to get the reactions that you want to make your biopolymer chains go a little bit faster. So again, my role as the curmudgeon is to say, this is an exceptional result. I hope I can convey to you a little bit, maybe not in technical language, but in graphic language, why the chemist views this as an exceptional result. And so you will understand why in the NASA astrobiology program over the years, as these various disciplines of chemists and who are the doubters or the deniers, the microbiologists, the geologists will interact in a way to bring forward the process that science is, which is, of course, the clash of contradicting cultures in an effort to come up with the truth, to inspire, of course, Americans' youth to go through the effort of studying science, so they knowing full well that there are these kinds of very interesting questions out there, like what is life and where might we find it, if not on Earth.
Thank you, Steve. I have a question for you. So, would you, as an organic chemist, consider replacing your graduate students with microbes to explore these reactions?
Many of my graduate students are undoubtedly watching, and I love you all, and I wouldn't think of replacing you.
Okay, fair enough answer. Okay, our next speaker is Dr. Pan Conrad. She's a planetary scientist at the Goddard Space Flight Center and also the deputy PI in an investigation that will be flown on the Mars Science Laboratory to be launched in a year from now. It's the first astrobiology mission since Viking, whose goal is to look for evidence of habitability and the potential for current and past life on Mars. Please, Pan.
Well, I don't think I'm going to classify myself either as curmudgeon or otherwise. My role in the astrobiology spectrum is to think about how we might predict the habitability of environments off the Earth. And the way I go about that is to see what I can learn about environments on the Earth and try to develop metrics for habitability. So I find this result delightful because it makes me have to expand my notion of what environmental constituents might enable habitability. So for example, if you just think about an environment in terms of what it's made of and how those things are arranged, you have a concept of an environment just like the chemical environment. Everything is a function of its constituents and how they're arranged. So what is really interesting about this result is if you can make a biomolecule that has substitutions in it, the properties have to change as a function of new constituents. So it opens up a whole new line of questioning. What might those changes be? What do they portend for the evolution of that chemistry? What do they mean about the environment? And by the same token, we might learn something new about habitable environments by understanding how organisms that are there adapt to the presence of new or limited chemical constituents. With respect to space exploration, this is a very interesting result again, because the implication is that we still don't know everything there is to know about what might make a habitable environment on another planet or a satellite of another planet. We have to increasingly broaden our perspective. So perhaps arsenic is not an essential component for habitability or for life, but it may be one that can be tolerated, and that opens up our perspective to try to understand what other potential components might be tolerated, or in fact even essential, that we presently haven't thought of.
Thank you very much. So I'd like to bring this all around and back to Felisa, for her to put her findings in a broader context for us and remind us of exactly what they are and their importance.
So let's remind us what we've learned here today. I'm interested in exceptions, and I think many of us are interested in those exceptions to the rules. Why are things constants in nature? That keeps me up at night. Why? I was probably a very difficult child in junior high and high school. But what I'll say is that that kind of openness to questions is part of what I want. I hope that the work of myself and my team that produced this. What I want to really reiterate is it's not about arsenic, and this isn't about Mono Lake. It's about thinking about life in a planetary context and asking questions, simple questions, with a simple experimental design. And so in like a bigger scale, let's go from the small and then we'll go into the abstract. All life on Earth required carbon, nitrogen, oxygen, hydrogen, phosphorus, and sulfur. So I've shown here today that we've discovered a microbe that can substitute arsenic for phosphorus in its major biomolecules. Not just DNA, but things like ATP, that many of those high school students out there I hope recognize, and also all sorts of other biomolecules. What does that suggest? It cracks open the door to the potential. You know, my niece asks me, how did we get here? And are we alone in the universe? And it's profound that we don't know the answers exactly to that yet. Maybe not in my lifetime, but maybe in her lifetime, she'll be able to answer that. But I hope my work serves as a proof of concept that we can experimentally test. And we need to look for that life here on Earth. Alien life here on Earth. And I've come to one of the most unusual places, an alien environment here on Earth, to look for life as we don't know it. Is a different kind of life here on Earth. Our current methods of detection would never see it. Why? Because we only know how to look for the life we do know. So if there's a shadow biosphere, if there's an alternative form of life even here on Earth, we'd never see it. In fact, it could be all around us. We're here at Mono Lake, not just because it looks otherworldly and is an amazing, beautiful place on Earth, but also because of the unique composition and chemistry that is here at Mono Lake. In particular, we know there are lots of different kinds of microbes. And for example, this lake is very high in arsenic. So there's very well-described microbes that breathe arsenate, a type of arsenic, like humans breathe oxygen. And there's also very unusual photosynthetic bacteria that do very interesting things with different kinds of compounds, not just like, for example, plants. But moreover, this lake, because of its high arsenic, will serve as a place that I may be able to test my hypothesis. So all life that we know of has exactly the same components. That is, if I grind you, a mosquito, a tree, and a microbe, and I analyze you with a certain kind of instrument, I will find that all life we know of has the same basic elements: carbon, nitrogen, hydrogen, oxygen, phosphorus, and sulfur. That's it. That's the unity of biochemistry. That's how I would say that. And that's very interesting, that all life we ever know has this basic composition. By saying it substitutes, by saying arsenic would substitute for phosphorus, I'm implying that phosphorus-based DNA is normal. It's the life we do know. So substituting arsenic would suggest a different way to be alive. And if that were true, what else might we be able to replace? And if you can replace it, could it have evolved completely independently? We haven't proven this, and we don't know if we'll actually find it. But it's worth a try to look, if we're going to go to Mars and Titan and look for life. What's to say that alien life, or even a life that evolved on Earth that was a second form of life, isn't here all around us? I can convince my colleagues and the scientific community that indeed we may have a microbe that can do something wildly different than we know of.